Hello there guys, welcome back to another epic inexorable maths video. In this video we're taking a look at how we might divide complex numbers. So we've got some complex number, I've written it in the notes here. We typically write complex numbers, at least one way that we can do it is in the form a plus bi, where a and b I've written are real numbers. That's all this means here, a, b are elements of the real numbers. That's what all of those signs mean, okay? So a and b are real, so 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, negative 0.7, pi, minus e, they're all real numbers, right? Any number that's not imaginary, not being times by I, is a real number. So where a and b are real numbers. And of course, I is the imaginary unit. I is the square root of minus 1. So we want to learn how to divide complex numbers by each other. So if we have, in general, let's say two complex numbers, we'll say the first complex number is a plus bi, and we want to divide that complex number by c plus di. Again, and c and d are also going to be real numbers. We want to divide these two numbers. Now, of course, you could just leave it like that, and sure, that's fine. It is what it is. It's just that it's not very helpful. What we want to do is we want to write this in the form e plus fi, basically. So another two real numbers, the real part is e, the imaginary part is fi. We want to write that in that form because it's a lot easier to sort of understand what's going on. So how do we do it? Well, if you're familiar with rationalizing the denominator, then this will be a breeze. It's the same idea. We're going to use basically the formula for the difference of two squares. Remember that the difference of two squares, if you have, for example, let's say x plus y times x minus y, that is identical to x squared minus y squared. Okay, that's just a fact. And it can go backwards as well. We can go from right to left as well. That's just a fact. That's true. That just comes from using FOIL and expanding things out. Now, why is this relevant right now? Well, I'll show you. Notice how we have an x squared and a y squared. Brilliant. Now, any number, as long as it is purely real or purely imaginary, when squared becomes real. Okay, so for example, if you square the number 3, that is 9, right? That's a real number. Same with any number, any real number, you square it, it's obviously going to be a real number, of course. But if you take, let's say, I, where I is an imaginary number, and you square that, that becomes minus 1, which is, minus 1 is a real number. Okay, cool. But if you just take any multiple of I, so for example 2i squared, that becomes minus 4, that's also a real number. And of course, in general, anything, any multiple of I, so we can just say like mi, well, so that just means any multiple of I, where m is also a real number, it just becomes minus m squared, doesn't it? That's how it works. And if m is a real number, then obviously m squared is a real number, which means minus m squared is also a real number, etc, etc, etc. So essentially we can use this formula. We realize that x squared, regardless of whether it's real or imaginary, is going to be real, and same goes for y squared. Cool. So we can use that fact in this way. What we're going to do is we're going to times the top and the bottom of this fraction here by the number 1. We're going to times it by 1, but we're going to do it in a funny way. We're going to times this number, and I'm going to zoom in for you guys. We're going to times this by 1 by actually timesing by just this. It's going to be c minus di divided by c minus di. Now, do you agree that that whole fraction, the whole thing, top and bottom, numerator and denominator, must just be equal to 1? Because it's one thing divided by itself. C minus di divided by itself. It's 1. It's the number 1. Why is that important? It doesn't change the value of the fraction. The whole thing, all of this, the whole thing, both fractions, it's just equal to this fraction here on the left. The whole thing, the numerator and denominator of that one on the left-hand side. If you times it by c minus di over c minus di, it's the same number. It's just being written in a different way. Cool. So now what we can do is we can use FOIL to expand this out. So how do we multiply fractions? Well, we simply times the numerators and the denominators together. So let's just write this all as one fraction to make it a little bit easier to understand what's going on here. C plus di times C minus di. And the reason why I chose C minus di, you might be thinking, well, where did that come from? What you do is you multiply by what we call the conjugate of whatever is on the denominator of the first fraction. The conjugate is simply the same number as what is on the denominator of the fraction, but instead of a plus sign in between the real and imaginary part, you replace it with a minus. If there's already a minus there, you replace it with a plus. You basically swap the minus with the plus. So you notice how C plus di is conjugates with C minus di. The reason why you do this is because you get the difference of two squares on the denominator. You can see that right here. C plus di, C minus di, that is the difference of two squares, which means you will end up with a real number on the denominator all of the time, regardless of what C and D are. Now, if we expand this out, what we get is, so first we get AC. Okay, AC, that's fine, that's good. And then we can do outside, so that's minus A times DI. Inside, that gives us plus B times CI. And then we do BI times minus DI. Okay, well, BI times DI is minus BD. So BI times minus DI is positive BD, and that's real. And that's divided by C squared, because that's C times C. And then I'll show you that this works. You do outside, so you get minus C times DI, inside plus C times DI. They cancel out, we'll see that in a second. And then we get DI times minus DI. Again, DI times DI gives you minus D squared. So DI times minus DI gives you positive D squared, just like that. Cool. And then we can simplify that a little bit as well. So I'm going to put the real parts together on that numerator. And I'm going to put the imaginary parts together like that. So I'm just factoring an I out of here. You guys can see that. So that you've got the AC here, then the BD. That's the AC, BD there. And then the imaginary parts just get grouped together. I swap the orders around, swap them around. So I put BC first, then AD. And I factored the I out just to show you that it's in the form A plus BI basically. And then you can notice how that cancels out, that cancels out. We end up with simply C squared plus D squared. Cool. And then that is essentially how we do it. This, if we separate this fraction out again, we end up with AC plus BD over C squared plus D squared plus BC minus AD over C squared plus D squared, and that bit is times by I. Cool. And you can clearly see here that this is in the form, we can say E plus FI, isn't it? Because where E and F are real numbers. Clearly, AC plus BD over C squared plus D squared, that's clearly a real number, there's no I involved. And BC minus AD over C squared plus D squared, that's real, but because it's being multiplied by I, it becomes imaginary. So this is in the form real number plus real number multiple of I, basically. So basically E plus FI sort of thing. This is the way that we divide complex numbers. So let's very quickly just do a cheeky little example so you can see exactly how this works. Okay guys, so we're going to work out what 2 plus I, that's a complex number, divided by 3 minus 5i is. Also a complex number. The first step that we do is we can rewrite this thing. So 2 plus I divided by 3 minus 5i. What we want to do is write it in the form, as I say, sort of like A plus BI or E plus FI, or it doesn't matter what the letters are, just in that form. What we do is we times it by the conjugate, remember, of 3 minus 5i, because that's on the denominator. The conjugate of 3 minus 5i is 3 plus 5i. Remember, you simply replace the minus with a plus or the plus with a minus, depending on what you have originally. And of course, we need to do the same thing on the top and the bottom, because this whole number here is the number 1, which means that it doesn't change the value of what we're basically timesing it by 1. It doesn't change the value of 2 plus I over 3 minus 5i, because we're just timesing by the number 1. So we can do this. But of course, it creates very convenient things because we get the difference of 2 squares on the denominator. It's the exact same principle behind rationalizing the denominator as well. So we can write this simply as one fraction because we're just timesing them. So we just times the numerators and the denominators together, just like this, just like that. Cool. And then all we do is we expand using FOIL. So 2 times 3 is 6. Then 2 times 5i, that gives us 10i. Then I times 3, that gives us 3i. And then I times 5i, that gives us minus 5. Careful with the pluses and minuses. 3 times 3, that gives us 9. We get minus 5i times 3. And 3 times 5i, they just cancel out with each other, so we don't need to write them. And then 5i times minus 5i, well, 5i times 5i is minus 25. So minus 5i times 5i is plus 25, just like that. That is equal then to 1 plus 13i over 34. And then we can split this up. We end up with 1 over 34 plus 13 over 34 times I, just like that. And that's right there is our complex number. That is the result of dividing those two complex numbers together, and it's nicely written in the form a plus bi, just like that. So a would be 1 over 34 and b would be 13 over 34. So that's all there is to it. If you enjoyed this video, if you found it helpful, make sure you like, subscribe and share with your friends, and I'll see you in the next video. Cheers.